Everybody? Ready? We start with the crash course. Alright, so we're gonna be crashing the data mining exam, hopefully not burning it on the way. And today, we're gonna do the following. We're gonna talk about the clustering, the anomaly detection, the classification, things you never studied before but you're gonna ask us now. A couple of exam questions, hopefully you already know how to solve them. And recommendations for the exam. I mean, except for, prayer and showing up on time and not drunk. Alright, let's start. Well, what's the thing with clustering? Basically, actually, you know what? First I'm going to ask, does anybody know or can explain to all of us what clustering is and what it's used for?
Groups of data points.
Alright? Yeah, we're grouping data points. Why are we grouping them?
On similarities.
Okay.
Or classification.
Exactly. And why are we doing this with the data? Any clue?
To have an overview.
Exactly. Because we are clustering it by similarity measures because we want to get some information about the data when we don't know anything about it. Alright, so basically, I have no clue what this data is about. I want to look for patterns, but I want to start somewhere. I don't want to try random stuff, right? That's why I use clustering. There's two types of clustering, hierarchical and, partitional. Does anybody know the difference between them?
For partitional, one data point can only be in one subset.
Okay, and for the hierarchical?
The opposite.
Exactly.
Yeah.
Now, they both have advantages and disadvantages. And we'll get into that.
Just a little bit more about clustering. You basically have four main types of different clusters. First one is just like the well-separated clusters that are as big as each other, so it's pretty easy to separate them. Then you have center-based clustering, where you can see that certain clusters are bigger than others, which is also not that big of a problem. Then you also have contiguous clusters, where you can see that certain clusterings are different shapes and sizes, let's say, because you can see basically a C that this is separate from the other points. And finally you have density based, where the density of the data points matters, and that makes the difference for the cluster also. Continue with the clustering algorithms.
The clustering algorithms, well, obviously it's a shit ton of them. Let's start with the k-means one. Does anybody know what k-means does? Not just the whole algorithm, but like the basic idea. What does it do?
I think it starts with arbitrary center points, then assigns all data points to their nearest cluster or center points, then readjust all center points to the mean of that cluster, and rinse and repeat.
Exactly what he said. Yes, so basically, just like a person would do, he starts with some random centers and looks around to see which point would fit into each cluster. Now, obviously, this sounds very simple, which means it's very prone to making some mistakes. The biggest one being the fact that when you choose the points randomly, there is a non-zero chance of choosing them next to each other for the initial means. Now, would that be helpful? Not really. Why? Because you're not really clustering anything next to each other. Also, the shapes of the clusters. Obviously, you're looking at what point is closest to each center. So if you have a cluster that's like a C, even if all of those points are technically the same, if you choose one mean at one point of the C and another mean at the other point of the C, you would have two clusters, which would obviously be incorrect in classifying it. Then you have hierarchical clustering, which, as we discussed, tries to fix some of the issues with just splitting everything into one separate cluster by choosing a hierarchy. So basically, at each point, you start with as many clusters as you have data points, and after each step, you unify two of the clusters up to a specific point, until you have one cluster for all of them, one technical cluster for all of them. And the final one is DB scan, or like density-based DB scan. Now, this doesn't look at the individual points, but at the relationship between the points. So for example, if you have, let's say, this thing, and I wanted to use, for example, k-means, no matter how you choose the centers, I'm going to have a disaster with the clustering, right? But if I look at this image, I see that the points that are related are kind of closely grouped together, right? They're more dense. The areas that are in the cluster are more dense than the areas outside the cluster. That's the principle. That's the guiding principle for dbScan. Obviously, for more details, you can look at the lectures. But the principal idea is that dbScan looks at how tightly are the points together inside the cluster as opposed to outside the cluster. Now, obviously, we kind of care to see if we are doing a good clustering or not, right? Obviously, because otherwise we cannot check them. Now, why is that important? Well, if you have random clustering, you lose the main point of what we discussed in the beginning, of getting information about the data. Well, there are different numerical measures. External measures, obviously, how well is my clustering, as in, are all data points that are the same cluster or not? Internal, meaning the structure of the cluster. For example, if I have two clusters, one that's kind of slightly mismatched, for example, I have a cluster with like 3 levels, that's good, and then I have another cluster with 50 hierarchies, that's a little bit better. It's kind of obvious that I would prefer the left one because it's easier to compute, right? Because we don't have infinite resources to compute the clusters. And relative index, well, that's when you want to compare two different clusterings. As in, okay, I used k-means, I used density, which one is better for my purpose, not in general.
Here, both internal and external indexes can be used.
Yep. And, well, there are different, obviously, metrics. The most important one, I think, is the entropy and purity, in our case, which are fancy ways of saying how much of this cluster is of the same thing. So if you remember decision trees and how they chose how to split by reducing entropy, it's basically the same principle.
I have a question. To what extent should we actually remember these formulas?
You don't have to remember any of the formulas as far as I'm aware. Most of the formulas are given. You should just be aware of how to use them.
Yeah.
And, yeah.
An important point, you don't have to remember all of them, most of them actually. I mean, you should probably know how to do like an average, a mean, or a weighted sum, but that's the basic stuff. But, you should still go over them, because seeing this kind of formula in the exam can get you confused if you've never seen it before.
Yeah.
And you lose valuable time.
Yeah, and we'll also have like one simple calculation of purity later in the exercises of the exam. So you can also see like how you actually use those formulas. Might be helpful. Yeah. Oh, yeah, that's my part, right? Yeah. Well, next up you have anomaly detection. This is different than noise. These are actually like patterns in the data that are supposed to be there instead of faulty measurements. There are different types of anomalies. Anomaly data at least. As you can see above, you have the time series data where you can see that there's a point in the data that does not really match the rest of the data points. You have it in images where you can see like certain images of the ones, of the zeros are not really quite as similar as the normal zeros and the ones. Some don't look like zeros or ones at all. If you look at this one, for example, it's a 6. This type of detection or data manipulation is unsupervised because you don't really have certain points that you want to specify as an anomaly and certain points not. This is more done based on the mean and the standard deviation. I'll get into that in a second. Here are some anomalies in data sets. As you can see, just the global and local differences in the outliers. I think that makes a lot of sense. So I'm not going to go into that one, but then you have univariate and multivariate outliers. This basically means that if you have multivariate outliers, you can clearly see that the outliers are based on both of the variables instead of a single variable, as you can see here. you have enclosed and full and the isolated cluster. It's not really that important. It's just more to get a visualization.
Sorry, but the graph with the univariate
No.
difference, they look like they're based on a different variable. They're outliers.
I can answer that. Alright, so moving to the univariate, it's not that just one variable varies. It's that you can tell it's an anomaly because one variable
Oh, so
is
it's
so,
about-
yeah.
okay.
So
So,
for example, this one kinda has the same y, but okay, x2, right? It kinda fits here, but the x1 is all over the place. This one is the opposite. The x is kinda close to the center of this one, but the y is obviously too far away. Because when you tell an anomaly, if you remember in frequency statistics, when you computed the standard deviation, SD, yeah, the deviation from the standard, it's kind of the same thing, right? Because you cannot really tell this anomaly no matter what, right? It's always about context, what the data you have. Anomaly detection is mostly about finding something that isn't like the rest of the data based on a metric, on a relative metric. There is nothing absolute about anomaly detection. And when it's multivariate, obviously, in this case, neither x1 nor x2 would fit inside this pattern, right? That's why it's multivariate.
No. Yeah, you have a couple different approaches. Mainly, the one that you initially grasp and think of is a statistical approach. Let's say you have a confidence interval. Just to get back to frequency statistics, you have a 95% confidence interval. Everything outside of that is basically rejected. It's basically the same thing with anomaly detection. You have some data, you fit it with a Gaussian with the mean and standard deviation, and everything that falls outside of your confidence interval is basically an anomaly. You have different types of tests or measurements for univariate data, so data with only a single variable, and multivariate data. The Groves test is for univariate data, and the mild distance is for multivariate data. You can also use k-nearest neighbor in this case. You have other clustering based methods, reconstruction based methods, and isolation forwards. You can look into that a little bit more deep in the lecture slides, but it's not really that important. We just want to mention it so you're aware of them. Here are some of the methods that you typically use when evaluating anomaly detection. It's also not that important, but the recall and the average, the recall and precision in general are the two main reasons or the main ways that you would use it in the exam for example, or just in general. Those two are quite good for evaluating anomaly detection.
One thing to mention before that, it's much easier to think about anomaly detection like a classification task, because if you look at it, the measurements are about the same, because this is a classification task specifically for classifying anomalies. Another thing I remember clearly from last year, precision, accuracy, recall were mentioned by name, not by formula, so it would be a good idea to remember these formulas. They're not that big, so it would be a good idea to memorize them.
Yeah, that's a good point. I think these are the only formulas that are not actually given.
Yeah,
But
so
yeah.
it would be good for you to know them by heart.
Yeah, I would definitely. Wait a minute. Did you guys have like this already in the first half? I don't think that would come up in the second half. No?
Yes, but it would give a multiple choice. It's a good idea to remember them. Anyway.
Yeah, I would still like glance over it at least. Yeah, then you basically have classification. You have the rule-based classifiers. So if you have a certain condition, then it is categorized as this. Let's say you have a list of people that are married or not married, and all the married ones say yes to a certain thing. Then you can make the statement basically that if this is true, then they say yes, basically. There are different ways of rule-based classification. There's a direct method called sequential covering. This basically starts with no rules and uses an objective function called the learn on rule function in order to get certain rules, and then goes through those rules until it is basically finished, and there are no classification problems anymore, and everything is classified. There is a specific rule growing algorithm that's called the Ripper. We will not go into a lot of detail here, and I would not recommend learning too much about it for this exam. It basically maximizes the information gain with the rules. It basically selects for the sequential covering algorithm. Then you also have indirect methods. One mentioned in slides is the C4.5 rules. It extracts rules from improved decision trees, compares rules until there is no further improvement that can be made, and it uses class-based ordering, so it divides the classification problems into subsets and then solves it on that basically. There are a lot of advantages with a rule-based classifier. It's basically really simple, computationally efficient, and it's easy to interpret. You can actually follow the logic with a rule-based classifier. New instances can be classified rapidly because you can just put an if-then statement and it's already done. Performance comparable to decision trees because it's basically a decision tree, just not written out. You have the formula for gain. It's again it's not really that important. You'll get the formula, but just to see it. This is basically what the sequential covering algorithm does. It basically, as you can see, you have certain data points, negative and positive. It basically thinks of a rule here, sees if that rule can be applied, and applies the rule. Then looks for the next spot or the next rule it can implement. In this case, this rule and then this rule, and until everything is basically solved. You have also have coverage and accuracy, which is basically the coverage of when somebody is single. That is no is basically 40%. So basically, the amount of data that you have where somebody is single or not single, so married, is equal to. Oh no, wait. I mean, where the status is single is 40%, because out of those 10 data points, 4 of them are single. If this person is single, if they would not cheat, that chance is 50%, because the amount of people that are single and actually cheat is 50%. So it's conditional. You also have instance.
I can keep doing this one. Alright, so basically, move one slide to the right. To the right, so to the instance class. Yeah, perfect.
Okay, cool.
Alright, so we have instance-based classifiers. Now, before we start on the details, can anybody tell me what makes them special enough that they have a different kind of classifiers? Something specific about them. No? Alright. Well, instance-based classifiers have the very, very special property. You could see that they don't have to be trained in the traditional sense. Alright, so basically, imagine the Chinese room that's given as an example in all courses, right? You're in that room, you have a book with all possible values your data could take. and you look into that book to see, okay, I have this value, what's the class? That's basically what instance-based classifiers attempt to do. So you have, let's say you have one data point that's each color of the rainbow, right? And you have a book and you're like, okay, I see this color, this is the name. And you get a color and you get asked, okay, what's the name? Well, obviously we're going to look into the book, here's the color, here's the name. Here you go. That's what instance-based classifiers do, which gives them a very big advantage of, well, not the training, and pretty good accuracy if you have a good data set, and a very big disadvantage of having to memorize the entire data set. Yes?
So do we need a discrete and not infinite amount of values that the data points can take?
Well, in reality, yes. In theory, no. That's the thing, right? Because in theory, you have all possible values. That's the assumption for the algorithm. You already know all possible forms your data can take, so you only have to look at the data you already have to classify a new data point. Now, obviously, in reality, this doesn't really make sense. That's why a rote learner wouldn't work, right? Because you have infinitely many forms your data can take in real life. But a nearest neighbor, though, could work, because you're not looking at something exactly the same, you're looking at something similar, which could, in theory, work, but then again, you run into the disadvantage of, well, having to memorize the entire data set with your model every time you want to use it. Which kind of works if you're classifying 2D things, right? But if you're classifying images, you need the image of every face of every human on Earth to classify them, doesn't really work anymore, right? Then we have probabilistic classifiers. Does anyone remember the Bayes rule from probability theory? I'm happy. Good. So basically, probabilistic classifiers go and say, well, I kind of suck at determinism, so I'm going to work with probabilities. So I'm going to start with the assumption that this data point has an equal chance of being in either class, and then I'm going to look at what information I know about this data point to bias my prediction. And at the end, I'm going to take a decision, which is basically, conditional probability and Bayes rule. And pretty much, in its most basic form, you have a table, well, a tabular, where you know about this data point, all the features, so all information about it, usually 0 and 1, or discrete values. And based on those, you compute the conditional probability, which is obviously, according to the Bayes rule, the probability of, well, the conditional probability reversed times the probability of that data point existing, which is just counting how many times data point you have in the training data sets, divided by the probability of all those preconditions existing. Right? So it's just basic probability theory. Now, obviously, there are a few problems that can arise from this. The first problem being, what if there is a situation where one class is incredibly rare, as in very rare? For example, a person that lives 200 years, right? It could happen, but it's incredibly rare, so you have no previous data on it. Well, in that case, if you were to go with the basic method, you would have an error here, right? Because the person can't, because you don't have any previous data on a person that has 200 years, this probability would be 0, and you would have an issue, right? Obviously, because you cannot divide by 0. Which is why you use estimators. Well, they're called estimators, but they're mostly used to smooth out this issue when you have no data points. And you have some of them. The original kind of kicks if you don't have any data points. Laplace assumes that every class has at most one data point, right? So every class starts by default with one data point before you count all data points. Which is why you add 1 here, because there's one data point in that class guaranteed, and you add C here. Pay attention, C, not 1, because you have one data point for each class, so obviously C data points total extra. And then you have the EM estimate, which doesn't start with one data point. It's similar to this one, to Laplace. It's just that you assume there is M data points in the class already, not just one, which is why you had this one here and this one here. And this one is the prior probability of A, so the prior probability of that class happening. So as I mentioned, there is a chance that there is a person that's 200 years old, but the chance is very little. So what this one does is take into account that, so you don't use one for all of them, right? That's the main idea.
Just
And
example.
well, let's start with the simple. Well, the calculations are easy enough to make, but let's think about the logic. Okay, so for example, let's say I want to know the probability. The probability that what the probability I want to know? Okay, fine. The probability that it's a mammal. Okay, so I get the data point, and I want the probability that this thing that I just picked is a mammal, right? And I have some information about it. Can it give birth? Can it fly? Lives in water? Has legs? Okay, its name. And how would I go about this? Well, what I'm interested about is the probability of m given, well, some stuff. Let's say I only know two things, x1, x2, and x3. Well, x1 could be the gives birth, x2 could be the fly, and x3 could be the lives in water, right? Well, if I want to calculate this, all I have to do is to inverse it via the base rule, given m multiplied by the probability of m divided by the probability of. Now, before I get to counting and calculating, can somebody tell me why there is the naive in the name of this classifier?
Sorry, why there is what?
Why it's called the naive-based classifier, not just Bayes classifier? Does anybody know? Any ideas?
Because it's simplified.
Okay, and how is it simplified?
Maybe because we're assuming independence of the variables?
Exactly. Yes, we are assuming that knowing that something can fly gives me no information about knowing if it can give birth, and vice versa, right? That's why it's naive-based classifier, which obviously doesn't really make sense, right? Because most things that can live in water don't really fly, for example. But that's what we assume. So in our case, to calculate this one, we would be able to do it like this, if I remember correctly, and I probably do. x1 with m times p of x2 1 m times p of x3 1 m times p of m divided by p of x1 times p of x2 times p of x3. Now, obviously, the main why it's called Bayes in naive-based classifier is because you update your beliefs based on what data you observe, right? Which tells you that to calculate things for this, you would need the number of data points with that specific property. So, for example, to calculate P of M, you would need a data point, now data points that are mammals in your training data set. And for x1, you will need the number of data points that have property x1, and vice versa for all of them. Yeah.
If we try to classify this way to a class that's not binary, but we have multiple, would we need to calculate for every class the probability and then pick the highest?
Okay, which one? So if you want to calculate this.
Okay, for now we only have two options, mammal or not mammal. So
Yeah.
if we have the probability, basically if it's higher than 0.5, it's mammal, otherwise not. What if we're trying to classify into multiple classes?
Yes, you're absolutely correct. You use max.
Okay,
So basically
yeah.
you want the maximum
So
one.
calculate all of them.
Well, it's technically called a soft max, not a hard max, because you are using less or equal, not less, right? You also count for the edge values.
Yeah.
Now, there is an important mention here. This is mostly trivia because you won't see it in the exam. But what would happen if you had a feature that isn't discrete? So, for example, instead of something that's from yes to no, it's something from 0 to 100. This is just a trivia question, but could anybody tell me what you would do in that case?
Create intervals.
Exactly, yeah. You would basically create some intervals, which then become your discrete variables. Now, I don't think this would ever appear in the exam, but if it appears, I need to know how to do it. Any questions about this one? No questions. Perfect. The probability exam is also coming up. Bayesian networks. Well, Bayesian networks are similar to Bayes classifier. It's just that, does anybody remember automatas from formal reasoning? Yeah, these things are similar to that one in how they're presented in memory. But what you have to know about these ones is that the actual Bayesian networks are used to learn the distribution of a data point, and from that one, obviously, you can also do classification, right? Because you look at which distribution would fit this data point best. But we don't need that for classification, right? We don't need all distribution, everything. We just need to be able to see, to be able to just check for each data point which distribution would fit in best without actually knowing the distribution, if it makes sense. That's why we do discriminative models that are focused on decision. So they're basically a summarized Bayesian network that's only used for deciding to which class is this particular point most likely to belong, right? Without learning the distribution as well, because that saves us on computational time and on complexity. That's pretty much the main point here. Well, logistic regression. Does anybody remember linear regression from frequentist statistics or from high school? Logistic regression is similar. It's just that you use a classifier that uses a log somewhat. That's pretty much it. And now neural networks. Well, this one is going to be fun. Now, can somebody tell me what a neural network is? General, very general.
It is a collection of neurons in multiple layers that then predict the outputs according to weights.
Mm-hmm. Yeah, that's a good summary. Now, what's the most important operation in a neural network?
Loss function?
Nah. The most basic, most important thing you need to be able to use a neural network.
Activation function.
Yes, that's one of them, but that's not the most basic one. What do you feed into the activation function? This is important.
Add all the inputs,
Exactly. And how do you add the input with the weights?
multiply.
Yeah, so matrix multiplication. You have to know how to do matrix multiplications. Because all this fancy stuff here you see here, you can delete all of this. This is a vector, this is another vector. You multiply them and sum them up and feed them into this. That's how neural networks work. That's how all neural networks work. Okay? So if you see this thing and get confused, imagine you're just seeing matrix multiplication from linear algebra. Now, let's get into the actual neural network stuff. Well, we initialize the weights, right? But what exactly are the weights? Can anybody tell me? Any ideas?
They are vectors that multiply every variable to scale them.
Okay, but what do they represent actually in the abstract sense?
Importance of the feature.
Yeah.
Yeah, exactly. So how important the feature is. Now, why do we need weights? Why do they even make sense? Because if I ask you, can this person win at basketball? There's a much higher importance on how tall this person is compared to what color their eyes have, right? So obviously you want to place more importance on the first one, which is why you have weights, which are randomly adjusted. Now, we need a way to evaluate how good a neural network does, right? Because otherwise we cannot discriminate them. You can probably recognize this one from the plethora of other cases where it's used. This is a squared error function. It's the most common one for the beginning. This basically just calculates the distances between your prediction and the actual truth and squares it to give more importance to high differences, right? Because if it wasn't squared, you would have a linear representation, which would put equal importance to small mistakes and big mistakes. But you really care about the big mistakes, like the humongous mistakes. You care a lot more about them the small one that are probably just noise. And afterwards, you obviously want to update the weights. Yeah, I don't think it was taught this year, but whoever took calculus 2 years ago probably remembers the gradient descent, right? Well, you're basically trying to minimize this error function. How you do that? Well, technically you calculate the gradient of this one, and then you calculate new values for the weights that each individually minimizes that error function. And you do that ad infinitum, or until you run out of money for the training. Now, there are some problems with the neural networks. Time consuming, because that's what Google burns forests, to have more data centers for them. Prone to overfitting, because they're very good at fitting on the data. They tend to learn patterns that aren't actually patterns. Vanishing gradient basically means, remember the gradient descent, the gradient gets too small and there's no actual improvement made step by step, so basically running in place and calculating. And as with any greedy solution, because this is a greedy solution, it can get stuck in local optima. So, any questions about neural networks? For example, how exactly do you choose the class? Can anybody tell me, in the end, this neural network, how does it actually decide which class the input belongs to?
Based on the threshold.
Okay? And how does the threshold work? The most basic one.
Well, the output has a certain interval. Let's say it goes from 0 to 1. We assign at certain intervals certain classes. So one class could be from 0 to 0.2.
Yeah. Either that way, or if it's a Bayesian, or if it is the Bayesian method, it takes the soft max from the output. So basically, you choose the probability that's the highest to occur. Now, another thing that's important is, as you mentioned, the activation function. Do you have it in the slide?
I'm not sure.
Yeah, perfect. Leave it here. Alright, so the activation function. Now, why do we need an activation function? Because as I mentioned, neural networks have matrix multiplication, right? And what does the matrix multiplication have as a property? It's linear, which means it's very good at classifying stuff like this. Let's say this I one class, this I one class, right? You draw a line, that's fine, that's perfect. But that's also what decision trees do, right? Not really important. However, if your data is like, let's say, like this, well, you won't really be able to draw this thing with a linear function, right? Which, here's what the activation function comes. Now, there are a lot of activation functions in our history, most of them pointers. The one that's mostly used now, if I remember correctly, is the soft something activation function, which is basically the value gets passed if x is bigger than a threshold, and it doesn't get activated at all. That's why it's called an activation function if x is smaller than threshold. This is the most common activation function in neural networks actually, and it provides nonlinearity, which basically means it allows you to draw these kind of things in the decision graph.
You want to go back or forward?
Any questions about activation functions? You should probably know the most basic one, so this one, you should know how it works by heart, so I don't think they will give it to you.
I don't think there's going to be a particular question asked about calculating with neural networks.
They might ask the purpose of an activation function, or they might ask the purpose of neural networks.
Yeah, they might ask the purpose of it, and
Or they might just give you 4 graphs and ask you, okay, which of these graphs belongs to a neural network? And you will know it's the graph with the random lines.
yeah, exactly. Not the actual calculations or anything like
Yeah.
that.
And obviously, there isn't just one kind of neural network. That was the most basic one. There are multiple kinds. Now, the thing is, you won't actually be asked to do anything with these neural networks in the exam. You will probably be asked information about the neural networks. So I suggest just going through them in the slides and familiarize them with the basic concepts. You probably won't be asked complex stuff, just the basic information why they're done like they're done. For example, if they ask you why convolutional neural networks are used, it's because in an image, for example, you classify an image by looking at specific symbols in the image. For example, you recognize a cat by the ears and the eyes, right? But if you feed the whole image to a neural network, it will not see the ears and the eyes, right? It will see just the whole image. Which is why convolutional neural networks take smaller parts of the image and consider them individually. That's the convolutional part of the convolutional neural network. Recurrent neural networks basically feed on input from before to generate input after. These are very useful in text-to-speech models because the words that follow in a sentence depend on all the words previously, right? Non-linear support vectors and support vector machines, they're basically, vectors, linear vectors. They're not very good at drawing these kind of lines, but they're much better than this thing. They're somewhere in the middle. Obviously, more information in the slides about these ones. Any specific question about these things?
Yeah, so does it use the first layer to extract, or the first few layers to extract where even the important bits are?
I'm sorry, which one?
The convolutional.
The convolutional neural network basically compact the data in order so the neural network can actually use it basically.
Well,
they do it mostly by pooling. You have something called max pooling where you basically take the max of the surrounding area, and average pooling is not that important yet.
Okay.
But like later.
Alright, so basically how they actually do it is just like shown in this image. As I said, it tries to summarize the data, right? But it can't really just, split the image into pieces, considering each individual piece, because it still needs to do matrix multiplication. Remember, this is the basic operation for all neural networks. So what it does is it chooses a smaller matrix. So let's say your image is something like this, right? It's a 4x4 image, right? And your neural network for next layers, it needs an image that's like this. It's a 2x2, right? So what it does, is it takes a mask and puts it over this one and computes the values. This is the first one. This is, I think, average. This is, I think, max pooling.
It really depends on what you want to do. Let's say you only look at surrounding area, so basically convolute it one time as you basically do here. Basically check the surrounding input as well as its own input, depending on what kind of pooling you do. This is basically the pooling. You have max pooling, where you basically take the max value of the surrounding area or itself, and you have the average pooling, where you just take the average of all those areas combined, and that makes it so you basically compact the data and still it still remains. You still have the important aspects of the data.
What is the value? How does it determine the value?
Well, that's what it was saying. So basically, you want to move from this one to this one, right? So obviously you can just copy paste the data. So that's why you take a window, for example, a 2x2 window. I forgot the actual name, but let's call it a window for now. Yeah.
Just for the top right one, let's say you have just really simple. So this is basically 0, 0, 0, 0, 0, 0, 1, 0, 0, and the rest of them, let's say, are 0 in general. Really doesn't matter, because like the ones you have here, they're 0 because you don't know what else it is. It's not.
That's padding.
That's padding.
Padding.
You're right. Sorry. Basically, you look at these 9, and you only want to calculate this one. You have average pooling, where you just take the average of all of them, so you just add them all up and you divide it by 9. You also have max pooling, where you just go through all the values and take the maximum of those values. In which case this here is 1, and yeah, basically like that. In this case they're all 1 because I put it here. But you basically take the max or the average. In most cases, it really depends on what kind of pooling you use for the convolutional neural network.
this should not be asked exactly in the exam.
This is not going to be asked in the
They
exam.
might ask what it does.
Yeah.
They won't ask you to calculate what it does. They're going to ask you why it does it and how it does it. It's probably going to be multiple choice, so just looking for the keywords, you know, pulling, summarize, and look at pieces of the data. Yeah?
In the Q&A before this one, they mentioned something about this, the shapes that this can produce, like circles or logs and things
Yes.
like that. Do you have which kind of functions give the shape?
Yeah, that's what I mentioned previously. They might ask you this, but they won't ask you what shape a convolutional neural network can generate compared to a linear neural network, because they kind of generate the same shape. They might ask you, okay, you have a decision tree and you have a neural network, which graph belongs to which algorithm? And you're going to know that decision trees usually tend to draw straight lines, while neural networks usually tend to draw also straight lines sometimes, but not necessarily. So for example, both of these can be drawn by a neural network, right? But this one cannot be drawn by a decision tree at all, ever. You can't. Now we reach the, well, not fun part, but an important part. Alright, so what do all classification methods have in common? They fucking suck in the real world. That's what they have in common. So one way of doing this is to have multiple methods contribute to the final result. So for example, instead of training one neural network, you train 100 and run out of money. But the result would be a lot better. That's basically what ensemble methods work. And we have two big ones. We have bagging and we have boosting. Not lol boosting, but actual boosting, the value. So for bagging, it's the easiest conclusion to which everybody arrives to. Okay, I take 100 classifiers, each one gives me one value, and I select the value that appears the most times, or the average value, whichever you prefer, right? And that kind of makes sense, but there's a small, very small problem. For this thing to make sense and to actually work, they would have to be completely independent. So each of them would have to be trained on completely independent data from the previous ones. Now this is not really realistic in reality, right? Because you have a limited training data set. Which is why for boosting, for bagging, you will use upsampling, or something similar to upsampling. So you will select from your training data set some data points to train that specific classification model. How you select them? Usually you select them by giving them equal probability of 1 over the number of data points in the data set. Now this is sampling with replacement, right? But because you sample pseudo-randomly, the final distribution of the data set you may use for that model should be similar to the one from the original data set. That's the idea behind it. Because if they're not independent and you train all of them on the same data set, for example, you train decision tree on the same data set, they're going to give the same answer, right? Because they will train the same way.
And this random picking with replacement, that is boosting?
That's bagging.
Bagging, okay.
Bagging, right. Because you cannot do bagging. No, there's no point in doing bagging if you use the same training data set for all of them, right? Because they give the same idea. Yeah.
Bagging is also where you upsample, right?
Yeah. As I said, it uses something similar to upsampling because you don't really lack the data points. You just want to reuse them for multiple data sets in a natural way, so without having to you picking them by hand. Now, boosting, you does things somewhat differently. Let's say you have a data point that's very, very hard to classify, right? It would make sense to focus the next models, on classifying just that data point. Which is why in boosting, specifically ADA boosting, you have 100 neural networks, but you don't train them in parallel. This is an important distinction. You don't train them in parallel, you train them sequentially. So first you take one of the models, train them on all the data, get the results, see the accuracy, and then you check the points that are wrong. Those points get a higher weight in the next model than the previous point. So if a point is correctly classified, then you don't care about it, right? Because it's already classified. If a point is wrongly classified, then you care a lot about it, because obviously the model doesn't work on that one. So that one gets a higher weight, which means that if, for example, you update a neural network, the changes made by that point are bigger than the changes made by the correctly classified point when you update the weights. That's the main principle in ADA boosting.
Yeah, that's an example.
And obviously there are formulas for this stuff. The formulas are on the slides. But that's the guiding principle behind it. And okay, how you go about it, the formulas differ from case to case, but the principle stays the same. Yeah. For example, let's take a random forest, which is basically decision trees, but a lot of them. Now, there are a lot of ways. There are two ways, as I said, of using this. First way, bagging, would mean train all of them in a pseudo data set you get from the original data set, right? All of them give you an answer, and use majority voting, which is basically, okay, which class appears most times, right? And that's your final answer. That's one way. Another way, can you go back for a second? Another way would be to just, instead of training all of them at the same time, you train all of them sequentially. You take the result from this one to calculate the weights of the input, train the next one, calculate the weights, train the next one, etc. until the end, and then use majority voting again to get the correct answer. Now we arrive at one simple problem, imbalanced data. When you did your project, you probably found data sets that had very few instances of a specific class, which kind of sucks. That means the model will be bad at it. Well, there's a few basic ways of accounting for this. The first way is oversample, which is creating data. For example, let's say you want to classify human faces, right? But you don't have enough human faces of this specific phenotype. For example, a specific tribe from the Amazon forest. You don't have enough faces, right? You could take an image generation algorithm, feed it the faces you already have, and it makes your faces that are similar but not the same. And that's how you would oversample. You create synthetic data. This one obviously will depend on the model that can make you the new data in a natural way. Otherwise, you can undersample, which is you try to remove the bias towards the data with a lot of points by just removing it. Now, this has the problem of making the data set smaller, which gives you less data to train your model on, which gives you worse results in general. You also have weight instances. This is the third point. If you remember in AdaBoost, the points that were wrongly classified have higher weight than the points that are correctly classified, right? In this case, the points that are smaller in the data, the points that are fewer in number get a higher weight than the points that are higher in number. The exact value depends on which formula you choose, which is in the slides if you're interested. But the main principle is that the few points you have, the more weight you have to give them so they have the same impact as the points from the more numerous class. For example, let's say let's say the example how the EU votes, for example, right? For all countries to have the same power in voting, countries with less people have to have more power per vote than the countries with a lot of people. That's the same idea for weighted instances. Data points from small classes have more power than data points from high classes with high number of individuals. Any questions? What's the time?
Half.
Okay.
Quarter.
We can take a 10-minute break, I think.
Gave you your break. Did any questions come up yet? Alright, yeah.
The similarity matrix, when they have the colors of the clusters, recognizing from the points in the clusters to where they are in the matrix, I don't understand that.
Can you, what exactly did I do?
When there's the matrix of the similarity matrix, it wasn't in these slides, it was
Okay.
in the, it's just like the colorful matrix,
Okay.
and if it's like nicely divided, then that is a cluster, yeah?
We can
Is there
look
like
up.
a specific question in an exam?
Yes, then, I don't know, but when we did the Q&A before this one, it came up and the
Oh, you mean like where they have like two lines extra? Stuff like that or not?
no.
Like multiple colors? Is that not
Yeah, they
just
have
two?
a lot of colors and then like squares in the matrix, which it's not a matrix with number, it's just colors.
Oh, it's like
It's similarity matrix.
can't actually.
I mean,
Maybe
I would have to see it again.
Wait, maybe we have this.
Do you mean the DB
That- that's
system,
one,
right?
This,
You mean Oh!
Right.
Yeah, and then having the points in the graph, like the actual clusters, and recognizing like there was a point with a number, and it was like, where is this point in the matrix? And finding it in the matrix.
I'm sorry, what exactly is the question?
Recognizing the point in the
I think
matrix,
that was from the first
and
one.
is that
No, that is from the second point.
yes, then like point 7, where is it in the matrix?
Well, in the matrix, you basically can see that there is a clear divide in the squares. It's pretty clear. But if it's like correctly classified, most of the time it's supposed to look like it has some kind of pattern, I guess. Instead of if you scroll down or scroll up, I think.
Yes,
This one, it's not really.
but like, how can we like realize the deletion distance, right? Like here, point 1 was point 1, and then saying like point 1 is like around here, and then point 7 is around here. But it was something like this point is like not very similar to this point, but it's kind of similar to the beginning, and that makes sense. This point is similar to me, but not everything else. But I cannot figure out. No. I mean, yeah, just for the yeah, like point B is higher here. You can index this one because it's only similar to itself, but not to anything else.
Yeah, you can just look at correlations and net idle or correlation. This is good to know the similarity matrix. Just real quick. If you have similarity matrices, I don't think it's going to come up, but if you do, if they're chaotic, if there are a lot of like lines through them, maybe I should look up a similarity matrix. You can answer the question. Which one did he ask?
Okay, so basically, if they say it in the Q&A, I would trust it like 90%.
Yeah.
The other 10% is if they have too many people passing. So, yeah, if they say that, then it's most likely not going to appear. Do you find one?
Yeah, I thought like maybe you need to like just really basic. Like if it's clean like this or this, basically you can see it in the data set itself that the clusters are rightly separated. If you have like random lines through it, like it looks like glitched, then you know these clusters are not rightly separated. This is also not the cleanest matrix, but you can definitely see that it clusters the data pretty well. No, of course not perfect, but if it didn't do a proper job, you would see a lot of like, let's say red lines or blue lines where they are not supposed to be. So just when you see it's clustered like this, the clusters themselves, then you know it's a good similarity matrix, and you know that the data is properly clustered. Yeah, I think that.
That's fine.
Okay.
Any other questions? Anything else? Any confusions? Leah?
Okay. Yeah. Okay.
No questions. Perfect. Let's go with the suffering.
We just have a couple exam questions that we thought would be good to go over.
Which you are gonna solve.
Yes, you guys are gonna solve.
Well, obviously, is the question statement.
This is just a question statement just to get into it. You have clustering algorithms, and you basically have a data set with 5 points, and this is the actual first question.
So, anybody wants to try their luck?
Just start with, we can just do like the min linking, the single links, if anybody's interested.
Okay.
I don't actually remember how the single link algorithm works.
That's then perfect if we're gonna solve this one, right?
Okay, basically they call it single linkage and complete linkage, but the only difference in how you do it is you either take the minimum distance or the maximum distance between them.
Mm-hmm.
That's basically the only difference. So, if anybody remembers, what was the starting point for hierarchical clustering? Where do we start?
Assign each point to its own cluster.
Yep. And afterwards, we have to start combining clusters until we have one big cluster that contains all of them. So I'm going to give you the starting point. Okay, so we start right here, and we have the points. x4 and x5. Now, each one has its own cluster, obviously, right? Well, minimum linkage or single link basically says combine the clusters that have the shortest distance between them. So, no, sorry. Single linkage basically says you take the closest point between the clusters. So let's say, for example, if I have, this is not related to this problem, but if I have these points and I have these two clusters, okay, single linkage is going to compare this to this because they're closest, I hope. Right? Complete linkage is going to compare this to this because they're furthest apart. That's the only difference. Otherwise, you always combine the two clusters that are closest together. Well, okay, after you get this measurement, you combine the clusters that have the smallest measurement with this rule. Does anybody want to give it an attempt?
You don't even have to draw the dendrogram. You can also just write down the step that you would link them.
But this would be easier. So, any questions?
Do you read it as like that the rows go to the column? Like
Well,
from x1 to x1, you have
X1
0?
to X1 is basically a distance of 0.
It
so
doesn't really matter because the distance is
So
the same either way.
The number is the distance.
Yeah.
Okay.
if you just like forget this part, this exact
Yeah.
similarity to this part.
Like the distances, for example, the distance from x1 to x3 is the same as from x3 to x1, right? Because otherwise it wouldn't make sense to cluster them. If that wasn't the case.
I can try to make the
Go ahead. We're gonna use minimum linkage, so this one.
I'll pick they're all single clusters, right?
Yeah.
Single points. I'll pick the first one that I can find, x2 and x5.
Yeah, you should still find the one with the smallest distance between them, which is x2 and x5. Yeah.
Yeah, although it's kind of hard to.
You can just.
Okay.
Yeah. Okay.
Yeah. Then there's another one, x5 with x2.
x5 and x2 are already clustered.
X3 you mean, right?
Like I would say that like from x5 to x2 is also very close.
Yeah, with X5
Yeah, but
and
x5 and
X2
x2 you already
yeah.
clustered them
Yeah.
together.
Okay. Oh wait, that's the same. Never
Yeah.
mind. Yeah. Then I would find the next smallest, which I think is x5 and x3.
Yeah.
But then, because we're doing minimal link, I could just find the closest. So I would include x3 in this cluster. I don't know how to write that.
Usually you can choose. Let's go with that.
Yeah.
Because there's no point in visualizing everything continuously.
So then, okay, x4 is now closest to x5. Include
Okay.
x4.
At the top here. Yep.
Mhm.
And then
then-
finally x1.
After.
That would be closest to.
Yeah. So that one. x2, x5,
Yeah, that makes sense.
x3, x4, and x1. Great! Congratulations.
Thank you.
Okay. Tell back.
Yeah. My bad. Okay.
Okay. Now, does anybody want to give their hand against MaxLink? So MaxLink works exactly the same way, but instead of choosing the point that's closest to your point in the cluster, you choose the point that's furthest from your point in the cluster. Yeah, come on.
When you said something for the first time, too well.
Okay. You can make an attempt, yes.
Yeah. So I go biggest, right?
Yeah,
Yes,
but
in the beginning it's the same because
two-
each cluster has 1 point.
yeah, there are no clusters formed yet, so you all take the minimum right now.
So,
So I take 1.
yeah, x2 and x5. Yeah, because they're the closest. Yep.
Yep. Now you still take the minimum, but you take the max out of the cluster and all points basically.
So basically you're choosing, when you select a point to
Yes.
compare against the cluster, you select the furthest point in the cluster to compare against the point of the closest, right? That's why it's max.
Yeah, but you still want to minimize the distance in general.
Yeah, so you would still choose, for example, in this case you would choose 2 1 cluster points because they're usually the closest. Well, let's say, for example,
That was wrong for me to ask.
wait. For example, let's see, now you have 4 clusters in your algorithm, right?
Yeah.
And you want to see the clusters that are closest together. All that when you compare 2 clusters, you choose the points from the 2 clusters that are furthest apart from each other. And that's your distance between the clusters. Okay? So let's start with x1 against the cluster of x2 and x5.
Yes.
Which point is furthest from x1 between x2 and x5? x2, right?
Yes.
Then the distance between the cluster x1 and the cluster of x2 and x5 is 10, not 1, because x2 is further away than x5. Okay, that's why it's maximum linkage.
Oh.
Got it? Let's try again with the x3, for example, now, and all the
Yeah.
clusters. Well, depends.
Do I not get it?
No, no, you
I think you should just call someone else because I just
No,
give
you
it a
you
go.
can do it. You can do it.
I mean, this is a confusion that everybody makes in the beginning, so it's a good idea to.
Yeah, that's why we chose this exercise in
Yeah.
particular.
Oh, okay. Because I got min, but then this is apparently a lot more difficult.
Yeah, basically, when you have a cluster, you basically group them together.
Yes.
You take the maximum distance from that cluster.
Yes.
So you basically group x2 and x5 for right now.
Because I want the smallest first.
Yeah.
You still want the smallest distance,
Yes.
but because they're clustered up, you basically take the maximum of that cluster. So let me just write it down, I guess. You want the minimal distance still,
Yes.
this, but use, let's say you have a distance I compared to the lower distance j,
Yes.
but this distance j is equal to x5 or x2.
Yes.
You basically take the maximum of those 2 distances instead of the minimum. Okay, I'm not writing this down correctly, but
Let me give
Yes.
an easier example. Alright, so here's what you're gonna do. In the exam, do
Yes.
not get confused about this. You will do
Yes.
it like this. Each step, you see which clusters you have, and you calculate the distance between all those clusters. Okay? Because in that way, it makes it much easier for you to select the smallest distance, and group them together. So let's give it a go. So in our case, we have 4 clusters. Cluster 1, which is x1, cluster 2, which is x2 and x5, cluster 3, which is x3, and cluster 4, which is x4. Okay, and obviously on the other side we still have C1, C2, C3, C4. The distance between the same cluster of 0, and now you just have to compute these ones. So let's give it a go with this one, between C1 and C2. Well, C1 is just x1, okay? C2 is x2 and x5. Now, since we're using max linkage, we're going to choose the furthest point between x2 and x5 compared with x1. That's the only difference. And that's your distance between the clusters. So between x2 and x5, the furthest point from x1 would be x2, right?
Yeah.
Which is 10, which means that distance between C1 and C2 is 10, not 9, right? Because x2 is further away from x1. That's why it's max linkage. Now, let's see, and obviously we put a 10 here as well because they're the same distance. Now let's see if they go between C1 and C3. There's no difference here because they're 1 point each.
So you take the min.
So you take the distance between the two.
Yeah, but do you take the minimum or the maximum?
So
You take the minimum.
you always take the minimum when you choose which classes to merge. But
Okay. But
the
then when you
distance-
have two, then you choose between
one that's
the
further away.
biggest and the one that you're comparing to.
yeah.
Mm-hmm.
Ah, okay.
Okay, so give it a go and make the paper. Come on.
Maybe it would help if you would show from the original table from where you take the values and what you are comparing.
Ah, yes. Well, I would just.
Well, how you got the 10, for example.
Okay.
Basically.
Let's. Can I do it? Perfect. Alright, so we're comparing cluster 1 to cluster 2. Okay? Since we're using maximum linkage, we want the furthest 2 points between these two clusters, right? So we want to maximize the intra-cluster distance. So for example, in C1 we have 1 point, right? So obviously we're going to compare everything against x1. And from the second cluster we have x2 and x5. Well, x2 has distance 10, x5 has distance 9. We want the point furthest away from x1, which is x2. So the actual distance between these two clusters, when we use max linkage, would be 10. Alright, so this one would be 10. Now, between C1 and C3, we have each cluster has 1 point, right? Which means that you don't have a choice to make. It's between x1 and x3. So it's going to be 8, right? Between C1 and C4, again, 1 point. So it's the same one, 4. Which means that it will also be 8 and 4 here. Now, C2 and C3. C2 has 2 points. C3 has 1 point. And I want the pair of points that has the greatest distance between them. Since C3 has 1 point, I want the greatest distance between x2 and x5. x2, x3 have distance 5. x5, x3 have distance 2. So obviously I'm going to choose this distance because I want max linkage. So the distance here is going to be 5. Yeah. Distance here is also going to be 5. Now I'm left with these two. C4, C2. C4 has 1 point, so I'm going to have x4. C2 has 2 points, x2 and x5. What is the point between these two that's furthest away from x4? x2 and x5 and x4. Well, x4 and x2 are distance 6, and x4 and x5 are distance 3. So this is the distance I'm going to check. I'm going to pick 6 here, which means there's going to be a 6 here as well. And now I have C3 and C4. They're 1 point each, so the distance is the same no matter how I take it. x3 and x4. x3 and x4, well, this between x3 and x4 is 7, so these two are going to be 7. Okay, so this is where the change happens when you use max linkage. Afterwards, you still pick the minimum value from these distances. The minimum value being 4. So I'm going to merge C1 and C4. Now, when I move to the next step, I'm going to have C1, which is going to be x1 and x4. C2, which is going to be x2 and x5. And C3, which is going to be x3. And obviously I'm going to have C1, C2, C3 here. Now, yeah, and now if you want to give it a try.
So then basically between 2 and 5, I look between 1 and 4, and
Yeah.
I compare the two biggest ones.
Yes. So x1 with x2 and x5, and x4 between x2
So I
and
need
x5,
to
which
look
one is
at
bigger?
4 possibilities.
Yes, that's how it works.
Okay, so x1, oh, it's just 10, right?
Yeah.
Because it's the biggest one.
Yeah, the biggest one. So that's 10. And the other one is also 10. Exactly. And now, between C1 and C3. Since C3 has 1 point, 8, right? 8 and 8. And now, between C2 and C3, there's just 1 point, so that's fine. No problem.
So 2, 3, 5, or 3. because it's either 5 or 2.
I think it's 5. Right? Right.
Either 5 or 1?
Because, at least how I understood it,
It's
because you're comparing 2 and 5 to 3, so you look,
Yeah.
wait, where is it? 3 to 2, and then 3 to 5, and 5 is the bigger one.
Yeah.
Yeah. Yeah.
Do you make it smaller again, though?
Yeah, you still select the smallest distance between these. So how you compute the distances, that's between max linkage and min linkage. You always choose the smallest distance here. So which one would be the smallest distance?
5.
Okay, so how would the clusters look like? We're not going to do the next step. Just the clusters.
Cluster 1 would be x1 and x1. Cluster 2 would be x2, x3,
3.
and x5.
Yeah. And afterwards you have to cluster them again using the same approach. Does it make sense? What the difference between min and max linkage? Any questions? No questions. Let's see if we fucked up. We're fine. Yeah, we got 2, 3, 5. We're fine. I mean, there's multiple ways to do this, I guess, but it's still fine. Yeah, it's fine. We're gonna be fine.
I mean, it looks pretty complicated. It's pretty doable. It's basically just applying the k-means algorithm as you normally do.
Which we will always call someone. Do you want to do this one as well?
I think they have enough.
Then do we have another victim? Volunteer. Someone else who wants to give a try to this one. Alright, a bit of question. How does k-means clustering work? We discussed this, so does anybody have an idea?
So first you initialize centroids.
That's what they were called.
However many we chose, so in this case 2.
Mm-hmm.
And then we assign each of the points to the closest centroid.
Mm-hmm.
And after that we recompute the center of the centroid. And we stop when the points don't change which centroids they're assigned to.
Yep. Exactly. Anybody wants to give it a go?
Sure. Can go again, like if someone else wants to go, that's just
Otherwise, we're
Anybody
gonna
else
pick
wants?
volunteers, right?
Yeah, we'll pick volunteers, yes.
Yeah.
Yeah, I can go. Okay. I'm not sure how I would approach this.
Well, it would be easier to just draw this on a
Yeah, okay, yeah, that makes sense. So,
and draw the centroid after each step.
M1. M2. D1. D2. I'm gonna just, call them D1 and D2.
And I think it would be best to just write to which centroid you assign which point after each step.
Yeah.
There's no point in writing like that.
So let's say M1 containing definitely D1 and D3. Just like visually.
Mm-hmm.
Then next step.
We recalculate the centroids.
Yeah. One would go to the mean between D1 and D3. This would be, what should I call it? Okay.
You can just call it M1 and erase the other M1. Okay? And
Yeah, they still contain the same.
yeah, if you contain the same points, now you have to reassign them based on the centroids.
Reassignment?
Yeah, so you look again at the points and see to which centroid each point belongs
Yeah,
to.
it's staying the same.
Yeah, I guess
Yeah.
in the same place. neighbors, right?
That's right.
Would this be the end? Or
Yeah.
It is the end.
As long as it
Nothing
goes-
else can change basically.
Yeah,
So
right.
if it stays the same, if it's the exact same calculation that you make twice in a row, basically means that you're done.
Right, how do you actually calculate it without like drawing it?
Without drawing, well, it depends on what distance
Okay.
measurement you want to use. Usually you use Euclidean or Manhattan. It's going to be specified. But the most common one is Euclidean.
Yeah.
Or extended Euclidean if you want to have more than 2 dimensions.
Yeah, just mean calculations is just taking the one mean and the other mean, so that's pretty simple. To get the centroids, you basically take the mean of the cluster points that you have gathered, and like we did before. By the way, any questions about this? No? Okay.
Oh, this is going to be fun.
Yeah, it's not gonna be. Yeah.
Okay, k nearest neighbors. Can anybody tell me how this one works? Someone else, maybe? Wants to give it a try? Yeah.
we have a set amount of neighbors that we're considering. I think we also have a threshold to how close these neighbors should be, and then we decide whether something is a centroid point or a neighbor point or an outlier, depending on how close they are to their neighbors.
Yes, that's how you would do anomaly detection too. For the classic k nearest neighbors algorithm, it basically works on the following principle. You pick an n, that's why it's called k and n. That n depends on the data set and how many points you have and the density of them. Afterwards, you choose the n nearest neighbors to the data point you want to classify, and you select the most common class among them. That's the most basic version. So in our case, you pick the point, f for example, and you look at the closest, how many neighbors? The closest neighbor, basically, it's just one neighbor. The closest neighbor to f would be, which one?
H, which is
You can look at the,
oh A, we're not.
A. Yeah. So it's A. So basically, if I use just one neighbor, I would say, okay, then clearly f is going to have the same class as A, which is positive. Okay, now to which question should I look for? If I know that f is equal to positive. Yep, so I don't give a crap about A and D anymore. I don't look at them. This makes you solve the exam faster. Now, let's go to G. What's the closest point to G? Look at the table. Yeah, because it's 0. That's interesting. Perfect. That means that G is, well, what's C? Yeah, then G is also negative.
So the answer is B.
Yep. But, go ahead.
Okay.
Yep, that's correct. You have to pay attention because it can also mean dissimilarity. Right? Because if it's cosine dissimilarity, so cosine similarity, not distance, it's the opposite. The bigger the value means they're closer together. Here it's cosine distance, so it's dissimilarity. So the smaller value is better. Or if it was similarity, the bigger value is better. Now they shouldn't have this kind of trap in the exam, but if it happens, just pay attention to what they're actually giving you.
Yeah.
Now we have 3 neighbors. Okay. Let's start again with F. What are the 3 closest points to F if I look at the table?
For F it would be A and C.
So, which class is most common among A, B, and C?
A and B are positive, so the majority is positive.
Okay, so which means that F is positive, right? So we only look at solutions B and C. Okay, for G, what are the 3 closest points to G?
Again, ABC.
Yeah, which is positive. So G is positive now. So what's the answer? C, no? Yeah. Yep. Any questions about how k nearest neighbors works? No questions. Perfect. Okay, let's go with this one. This one, well, we want to calculate the probability of the clustering, I assume, no? Yes.
Yes.
Well, you can make use of the coloring, right?
Yeah, you can basically make use of the coloring. You can take into consideration the cluster and the purity of the cluster itself, like the amount of true positives in the cluster divided by the amount of totals in the cluster. And you also have to take a look at the collective cluster in general, like how many of these are actually correctly classified. And that's how you basically calculate the purity.
And one more thing, keep in mind here it mentions k is the number of clusters, but in hierarchical clustering this is variable, right? Because you can pick this level and you have more clusters than this level. The purity of the clustering should be similar, should actually be the same. But since they give you actually the hint of computing these two, you take k equals to 2 and you compute for these two clusters.
Yeah.
And I mean, it's just computing.
Anybody got an idea?
Anyone wants to give it a try?
I mean, this is not the most for hand liggend.
It's just plugging in the values.
Yeah.
Alright.
I can guess the value, for example, Pij. I would assume that because most things in the green class are B, I would assume that A are the wrongly classified numbers, which are 2 of them.
Yeah.
That would be Pij.
Well, they actually give you the formula with how it works.
Yeah.
It's just that you have to compute it. But
Okay, so it's 2 over the amount of items in the green class?
yeah, Pij would be the fraction of objects in cluster I that belong to cluster J. To class J. Yeah.
May I write it out?
Yeah, alright.
Just like the formula itself.
Just not in the projection.
So you basically have the clusters that are separated already, and you have amount of data points. In this case, I know it's on the top of my head. I think this is 16, this is 14 in total, and so you have like 30 in total. So you know that M is 30, and that for N1 it's 16 or maybe 14. I don't know. Little math. Top of my head. You have the max E1 and the lower one. Max E3. So you basically want to calculate, or you still need to calculate the probability of this cluster actually being correct. Yeah, so basically the amount of total the biggest group in the cluster, so the biggest amount of classifications that are right. And then in this case you can actually see that it is everything except for 2 for B, and for A it's
So then it's just what's number 16.
yeah.
What is the max J operation over the Pij?
Okay, max J basically say calculate all Pij is for possible J and pick the biggest one.
Yeah.
But there are multiple Pijs.
Yeah, because you have Pi1, so basically
But you calculate all of them as sum them.
no. You sum over the clusters, but here you pick the max for that specific cluster. So for example, look just at this one, and you have 2 Pijs. You have the Pij where J is for class A, this one,
Oh.
and then you have the Pij for class B.
So you
select the
assume
biggest
that the
one.
most frequent value is the class that it's supposed to be.
Yeah, that's why you use the purity like this, right?
And anybody wants to guess the second one? The second highest
Nine.
probability?
Wait, 11 times divided by 30?
Not divided by 30, but in
Oh,
this
divided by
case,
2.
yeah. No, 14 in this case, but yeah. And that's roughly equals to 55, 6. And that's basically how you calculate the purity of
yeah. Class A. Any questions about this one? This is an example of how formulas are going to be given in the exam. No questions? Perfect. Let's move on.
I think that's it. Yep.
Recommendations. Well, obviously, read the questions, careful for things, for example, similarity versus distance, or Manhattan distance versus Euclidean distance. Don't read over words, because they might just change something very small that changes the result completely. Double check your calculations. If possible, graph the values, either like 2-dimensional, 3-dimensional, or not just 2-dimensional. Graph the values if possible. Keep calm. Memorize the small formulas like purity, entropy, Euclidean distance. Yeah.
Also like cosine distance.
Well, they should give it, but it's not that difficult. So if you have the time, sure, memorize as many as possible, because it's faster for you if you already know the formula.
If you really want to go for a 10, I would recommend doing the book exercises, because I have not seen a single exercise or exam question that has not already been given in the exercise and in the practice exams that you already have access to. So that's my recommendation.
Anything else? Any other questions?
Mhm.
Well,